This tutorial is on frame of reference, which can be easily defined as the point of view. It defines what is not moving, which might be a very bizarre way of describing things. But for instance, let's say that you are flying in an airplane and you look at the person beside you, might be talking on the phone. And as you're talking on the phone, you describe this person sitting beside you and you say, well, the person's not moving, they're just sitting there. Obviously, we understand that the airplane is moving, and hence they are moving as well. But according to our point of view, our frame of reference, we would define that person as not moving. Similarly, if I look at a chair in the room, I would say that the chair is not moving. Understand, though, that the Earth is rotating, and it's also revolving around the sun, and so of course the chair is moving, as everything in the universe is really moving. But in order to describe motion, we have to first define what we are going to consider not moving. What is our frame of reference? The most common frame of reference is the Earth. We say that the Earth is not moving, and so therefore anything moving relative to the Earth is. So if a car is sitting stationary on the Earth, we say it's not moving. But then as it starts to move left or right, we would say that it is moving. But we have to define the Earth as not moving. In most circumstances, that's what we do, unless we are inside something like a car or an airplane. So we're going to look at a couple problems here. One very basic says we have a passenger at the rear of a train traveling at 15 meters per second relative to the Earth, throws a baseball at the speed of 20 meters per second in the direction opposite of the motion of the train. What is the velocity of the baseball relative to the Earth as it leaves the thrower's hand? So somebody inside the train, according to the train's frame of reference, that person would describe the baseball as moving at 20 meters per second. But somebody standing outside the train looking at it, right here, would not describe the baseball as moving at 20 meters per second because the train is moving forward at 15 meters per second while it is being thrown. So how fast would this person standing on the Earth see the baseball moving as it is thrown? Well, because these two vectors are in opposite direction, we're going to combine them. Being in opposite directions, we subtract. So we say that the 20 meters per second of the baseball subtracted from the 15 meters per second the train is moving gives us that the baseball is moving 5 meters per second, and in this case to the left. It's more of a logic answer than anything else. There's no formulas in this section. We just kind of reason through these problems. Our second problem that we're going to look at is a ferry crossing a river. If the ferry is headed due north with a speed of 3.5 meters per second relative to the water, and the river's velocity is 3 meters per second to the east, what will the boat's velocity be relative to the Earth? So here we have a boat that can move at 3.5 meters per second and tries to go straight across this river. However, the current of the river takes the boat down. And so the overall direction the boat travels is at an angle because of the current of the river. So we want to know how fast this boat is actually traveling. The river of the current speeds the boat up a little bit. But because it's not in the same direction of the boat, it's not 6.5 meters per second. Instead, we are going to have to use our Pythagorean theorem to get this speed of the boat. But we also want to know, since we are asked what is the boat's velocity, that means a direction as well. So we have a right triangle, we want to find the hypotenuse, and we want to find the angle. So to do so, to find that velocity, we're going to use the Pythagorean theorem, which says that v squared is equal to 3.5 squared plus 3 squared. This gives us a velocity, at least in magnitude, of 4.6 meters per second. But we also need that direction. So to get the direction, we know the opposite and the adjacent side. So we're going to use our inverse tangent. Again, to get angles, we use the inverse trig function. So the inverse tangent of the opposite, which is 3, divided by the adjacent, which is 3.5. So we solve for that angle, and that angle comes out to be 40.8 degrees. And so that is our overall answer. We can either write it in these two spots since we have it labeled in our diagram, or you can just write it as one if you like. Our velocity is 4.6 meters per second at an angle, so I'll duplicate that direction, and it's relative to my vertical line. So I'll draw a vertical dotted line, and that is an angle of 40.8 degrees. Put a box around it so we know where our answer is located.